So this is our third lecture on soil deformation. I want to start with a case history about the BURJ KHALIFA. And I'm going to turn the lights off and then we'll look it up. So the BURJ KHALIFA is the tallest structure on our planet. It's 828 meters high, and it was completed in 2009. It's located in Dubai, in the United Arab Emirates. These are the credits of where we found the information. I want to acknowledge my colleague, Yu Chen, who helped put all this together. He's actually behind the camera right now. So these are the credits. These are the tallest structures in the world today, 2020. On the left-hand side is the tallest, or to be the tallest, because it's kind of stopped. The construction is right about to here. But that's the Kingdom Tower in Jeddah. And then the one I'm going to talk about is currently the tallest one at 828 meters in Dubai. And you see how many large structures, tall structures we have. Even the number 20 is at 500 meters tall. So the BURJ KHALIFA, BURJ means tower. The BURJ KHALIFA is 828 meters high. It weighs 4,400 meganewtons. The area of the base of the tower, the foundation if you wish, is 3,400 square meters, and the average pressure under the tower is therefore about 1,300 kilopascal. Remember, we've talked before about the Tower of Pisa being around 500, Washington Monument about 500. Today, we probably, on soils, we wouldn't put more than about 200 on the shallow foundation, typical. But this one is actually on rock, and so that's why the pressure is so high at 1,300 kilopascal. It was built on a pile foundation, deep foundation. The piles are 50 meters deep below the mat foundation. So a mat was placed, there was an excavation about 15 meters deep below ground surface, and then the mat was placed, the piles being below that mat. So the average soil/rock modulus is about 700 megapascal. You know, we've talked about the modulus of soil being between 1 and 100 megapascal. This one is obviously beyond soils, and soft rock around 700 megapascal. The pile capacity was around 30 meganewtons, which is huge actually for a pile. Not a record number, but a very large capacity. So the geotechnical investigation took place. The rock is a calcareous rock. It has sandstone, siltstone layers. The water table is 2.7 meters below the ground surface. About 33 boreholes were used for the investigation. 7 of the piles were load tested. We'll see that in a minute. And 60 pressure meter tests were carried out. We mentioned the pressure meter in the last lecture as a tool that's quite helpful in obtaining the modulus. And these tests were used to calculate the settlement of that huge tower. And the original plan was for a 1.6 kilometer tall tower, but then it ended up being 800 or 0.3 kilometers high. This is a soil modulus profile. You see a lot of variation. There are different types of tests. If you were able to read all this, you would see that there's a lot of pressure meter tests. There's also some triaxial tests, some resonant column, and then some geophysical tests. And each one of those gives a certain modulus. You can see the variation is significant. It goes here from some 12,000 megapascal down to maybe 100 megapascal. And the difficulty, of course, for the engineer in charge of this, calculating the settlement of this large tower, is to pick the right modulus out of all those tests that were performed. The foundation, as I mentioned, is a mat that's 3.7 meter thick, and below the mat you have 194 board piles. They are 47, so I say close to 50 meter long and 1.5 meter in diameter. So it's not, again, not a record, but a large diameter anyway. And the workload on the piles was 30 meganewton with a factor of safety of at least 2. So here is a cartoon of the tower with the foundation to scale. And you can see that even though those piles are 50 meter deep, they're very small compared to the length of the tower. But it still looks reasonable, and that's one thing that I've told you many times. Make sure you start with a diagram to scale to get a sense of whether things are out of proportion or maybe pick up on some potential problem. I actually went to visit the tower, and I didn't go to the top. I went to the observation deck, which is around here somewhere, 450 meter high, and the elevators are extremely smooth. You get the feeling that you're not moving, and the only reason you know you're moving is because your ears are popping due to the difference in pressure. So it's pretty impressive. And again, I didn't go to the top. So here is the imprint of the foundation. It's a tri-star imprint. You can see all the piles that are those 1.5 meter diameter pile that are located, distributed around. Here's a rendition of the piles under the mat. The mat is right here, and the piles, you can see them underneath it. Here's the size of those board piles with all the reinforcement going down to 50 meters. They were load tested, and these pile load tests were, large pile load tests. You had to go to about 6,000 tons, which is 6 meganewton, to test the piles for the close to 2 times the working load. These are pile load test results. I'll pass on this. And so this is a contour of the piles, and this is the red is 37 meganewton, and you can see the piles on the outside are more heavily loaded than the piles in the center, probably due in part to the overturning moment that loads the outside piles. Back to the solid modulus profile. Again, the need to select a profile to be able to calculate the settlement. This is isolating the pressure meter test results, well, actually with some of the other results, and then the final selection by the engineer to be able to obtain the design profile. So somewhat conservative, but not all the way down to the bottom. So obviously it takes a lot of experience to be able to make those types of selection. This is estimating the settlement using the finite element method, and the settlement across the width here, and you can see the dishing effect of the foundation. And then monitoring the settlement of that large structure as a function of construction the settlement takes place, it increases, and this is the end of construction right here. You're looking at some 43 millimeters of settlement. Here is about a little bit less than 2 inches along the cross section of the foundation. And then this is the prediction of the settlement, so end of construction, but as a function of time, there could be some creep. So the prediction is quite good for a structure like this. Nevertheless, to see an 828 meter tall tower set on only less than 2 inches is pretty amazing. So I wanted to include this because we just looked at that settlement equation the last lecture, I 1 minus nu squared PB over E, where S is settlement, I is the influence factor, Poisson's ratio, design pressure, width of the foundation, and then elastic modulus. So I was 1.3, you find this in the book. The pressure we discussed is about 1300 kilopascal. The modulus from the profile, average modulus, 700 megapascal. So if you apply that equation, you multiply everything, and you find 43 millimeters, which is remarkably close to the actual measurement. Obviously, the selection of this modulus here, we had the answer, so we were able to match one and the other. But the 700 megapascal is kind of an average value within that pressure meter profile. So here is the foundation being constructed. You can see all the board piles here, and then the mat, the reinforcement for the mat is being laid out. And then the mat is completed. So this is January 2005 right here. And then it keeps going. September 2005, January 2006. January 2006, December 2006, and then on and on and on. And coming in 2007, December 2007, January 2008, December 2008, and then December 2009, the completion of the tower. So, when I look at those fantastic structures, and I say to myself, these are my civil engineering colleagues that are building those structures, and that is mighty impressive. And I keep being so excited to be a civil engineer that it really amazes me that civil engineers actually accomplish these remarkable feats. 828 meters, and a new one coming to 1 kilometer. This is mind-boggling. All right, let me get back to put the light on, turn this off, and then blank screen, turn this off. So this is a remarkable example of soil deformation. Let me continue then with that third lecture on soil deformation. Soil deformation. We've seen in the first two lectures the importance of the modulus and how to calculate it. I want to talk about, and you can, I told you can get it from the triaxial test, you can get it from the pressure meter test. I want to talk today about another test called the consolidation test. The consolidation test goes back a long way. Consolidation test. And this test consists of placing a sample in a steel ring. And the sample is placed in the steel ring. We mentioned it the last time when we did this calculation of modulus, and we apply a load on top of this disc of soil through a platen, a top, and we apply a stress sigma. And we measure the amount of compression that the sample experiences. So this is delta H, and the initial height is H. So the way we do this is that we increase the load in steps. I mean, there are several procedures, but let's put sigma here versus time. And then the loading is in steps. So we'll start with a load, and then after a while we increase the load, and then we increase the load, and then we increase the load, and so on. And the amount of time that we apply each load is 24 hours. So if this is A, B, C, D steps, the step B, I'm going to be recording the settlement, actually the strain. I'm going to put epsilon equal delta H over H here as a function of time. During those 24 hours. So the time is going to go from 0 to 24 hours. Time in hours. And then the time in hours is, and then the strain, obviously, as I apply the load, the strain is going to increase and it's going to slow down. And the idea is that 24 hours is long enough for all the compression to have taken place. The process of consolidation is associated, so let me go back a minute here. These are typically run for saturated, fine-grained soils. Okay? But it's also run for unsaturated soils as well. So those saturated soils, when you apply the load, it's very difficult for the water to get out very easily, very quickly. So you apply the load, the water is stressed and it goes up into pressure, the water pressure goes up, the water stress. And then as a function of time, it drains out through the top and through the bottom. And so the stress goes, the water stress goes up, and then it goes down, 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 until it comes back to essentially zero. And the choice of 24 hours is that considering the thickness here, which is usually around 25 millimeters. Okay? So about that thick, full scale. And the idea is that after 24 hours, then you have come to equilibrium. So this is an equilibrium point. And so at that point, you obtain here epsilon, and I guess it was step B, so we'll call it epsilon B. And the stress right here was sigma B, corresponding to step B. So this is sigma B. This is the strain time curve for a stress sigma B. And because at the end, I'm assuming that after 24 hours I've got 0 water stress left, then sigma B is also going to be sigma prime B. So in the end, by repeating all those steps, we're going to end up with a bunch of epsilon B, C, D at equilibrium, and we will be able to plot a stress strain curve, which is going to show sigma prime versus epsilon. And point by point, we're going to put here sigma prime A and epsilon A, sigma prime A, epsilon A, and we're going to put sigma prime B and epsilon B and C and so on, and that way we describe the curve. So 1, 2, 3, 4, 5, and so on like this. All right, that's the stress strain curve. And here I put it on the normal scale, arithmetic scale, and you can see that there's something a little bit strange with that stress strain curve. You know, all the stress strain curve I've plotted so far have always been something like this. And this stress strain curve actually curls the other way. And the reason it does that is because the soil is confined into a steel ring. So the more you push on the soil, the more the soil pushes on the steel ring, and the steel ring is not going to break at the type of stresses that we're talking about. So here, this is the soil, and the more you go, the more this is the steel ring. So when you use that test, be careful that you don't go too far, because there is no steel ring under the BURJ KHALIFA or the Washington Monument, but there is a steel ring in the lab. So keep that in mind. Actually, this is a typical way of plotting the stress strain curve, but we don't plot it that way. What we plot is a curve that has log of sigma prime on the horizontal axis, and we plot log epsilon, actually we plot epsilon on the log scale on the vertical axis. And when you do that, it deforms the curve into something that, so you have the same points, and the curve looks something like that. Okay? But it is a stress strain curve. I mean, the curve that we get from a consolidation test is a stress strain curve, and therefore we get all the advantages that you get from a stress strain curve, including calculating compression. And but what's critically important is, and we'll see that in a minute when we talk about settlement calculation, is anytime you're going to use the results of lab tests, in situ tests, or theories, understand the conditions that they are representing. As I mentioned, in this case, if you go too far, you're going to test the steel ring, not the soil. In the pressure meter, you're moving in this direction, not in this direction. Some people argue that. In the triaxial test, you have a small, so there are some limitations and advantages on each one of them. And as an engineer, you need to think about those things to try to choose the one that really fits your problem the best. And if you're not too sure, then run a couple of tests. Don't do just one test. That's what you saw the BURJ KHALIFA. There was some resonant column, triaxial test, pressure meter test, geophysics test, and then looking at the cross-section, you know, some variation, and then you got to pick a design profile, which is not the easiest part, but a lot of people are working on this. All right, so this is the type of curve, stress strain curve that we get. Each one of those points is an equilibrium point at the end of the 24-hour loading in that particular instrument. From this curve, we get a number of things, a number of information. Often we will look at this curve and say, all right, here I have something that's reasonably linear, and here I have something that's reasonably linear. And some people have made some advanced construction techniques that can be used to find this important point right here that corresponds to what we call the pre-consolidation pressure. And that's a very important pressure for several reasons. One of which is, if you can stay below that pressure when it comes to the stress that you're generating under the structure, then you're going to be in pretty good shape, because you can see that the epsilon here is quite small compared to the increase in stress. But when you start going beyond that pre-consolidation pressure, then you really dive into a different type of behavior where an increase in stress leads to a fairly large increase in strength. So it's a little bit like a yield pressure, if you wish, as we use in concrete and steel and so on. We also define that slope right here. Let me first go through a separate exercise. Let's say that, and the reason is that often people put the void ratio here instead of a strain, and so I need to create the link between the void ratio and the strain. Imagine that we have a sample, so I'm doing a three-phase diagram, but I'm not going to go three-phase, I'm just going to do two-phase. So these are the solids right here, and these are the voids. So this is the initial state, and I'm going to make the solid volume proportional to a unit value, 1 cubic meter, if you wish. Then in that case, by definition, the void ratio is the volume of voids divided by the volume of solids. So therefore, if this is 1, then this is E. When the material compresses, well, in there, I compress the material, then that whole picture is going to decrease in height. And I get to a second picture that looks like this. This is still the solid. The solid is a solid block of rock, so I cannot compress that. So this solid piece of block is still 1, while the voids have decreased. So I'll put V1, V2, and then I'll have E1, and then this is going to be 1 again because it hasn't changed, but this has decreased and it has become E2. And you can see that the change in height of this diagram is E1 minus E2, or delta E, if you wish. And so the strain epsilon is going to be E1 minus E2 divided by the initial height, which is 1 plus E1, or delta E over 1 plus E initial E1. So that's the link between the strain and the change in void ratio. So you can either put the strain here or the void ratio. It depends on the company where you work. So that now that we have the link between one and the other, I can define a number of things. C sub C is the slope of the sigma prime versus void ratio. So it's going to be delta E over delta log sigma prime. I'm sorry, I made a mistake here. This is not log sigma prime, this is sigma prime. This is not log epsilon, it's epsilon. So it's a semi-log plot. This is a natural scale, this is a log scale. Okay? So C sub C is delta E over delta log sigma prime. And I told you that delta E is epsilon times 1 plus E, and this is equal to delta H over H, right? Compression divided by initial height. So this leads to delta H, the compression, being equal to, and that's the initial height, and we'll call the E1 the E0. So I've got equals H0 delta E over 1 plus E0, E1 and E0 being the same thing, the initial void ratio. Now, the delta E is going to be C sub C delta log sigma prime. So I've got H0 over 1 plus E0 times C sub C delta log sigma prime. And then delta log sigma prime is log sigma prime 1 minus log sigma prime 2, or the ratio of the two logs. So that's going to be H0 1 plus E0, C sub C log of the stress sigma prime after the loading by the structure, for example, divided by sigma prime before the loading. Okay? So that's the one of the root equations for calculating the compression of the layer using that slope right here. So this slope, in this case, it is not C sub C, because you see C sub C is with the void ratio, and I've put the, but this is related to, so I'll put it here, related to C sub C. This one is related to C sub R, because this is a recompression part of the curve. And so these are the three things that are defined on that curve: C sub R, C sub C, and sigma prime P. So if you change this to the void ratio, then this is C sub R, this is C sub C, and this is sigma prime P. So the important definition is right here. All right. Now let me talk a little bit about the over-consolidation ratio. So I'm going to recreate this curve right here. And remember, that curve was and I'm going to do it this time, log sigma prime versus void ratio. And the curve looked like this. And so in that case, this was C sub C if this was 1, and this was C sub R is if this was 1. And then right here was the very important sigma prime pre-consolidation pressure. And pre-consolidation pressure is in terms of effective stress. This is the result of a consolidation test that was done from a sample taken from the field. This sample may have been taken from 10 meters deep. On that sample, before we took it out, there was a certain amount of vertical effective stress. And that vertical effective stress in the field, so I'll put it here, this was in the field at this point M, and in the field, under that overburden pressure, we had sigma prime 0 vertical. And you don't have to calculate that. It's the total stress minus alpha UW, or if it's saturated, simply minus UW. So that's sigma prime OV. If sigma prime OV is here, so I can plot sigma prime OV on this axis here. If sigma prime OV is less than sigma prime P, that means that sometime in the past, the stress on the soil was higher than today. We talked earlier about Chicago and ice and so on. And so that's an indication that the soil has been over-consolidated. So we call this over-consolidated soil, or OC. If sigma prime OV is equal to sigma prime P, approximately, we talk about a soil being normally consolidated, or NC. And there's a big difference between we further call the over-consolidation ratio, OCR, equal sigma prime P over sigma prime OV. And as I said, this is the over-consolidation ratio. And this OCR plays an important role in many of the correlations that we develop in soil mechanics. This equation right here that goes delta H equal to this will depend on whether your increase in stress is going to be keeping the pressure here or on this side. Because if you have a situation, there can be two situations. If you have this situation, log sigma prime is here, and this is E or epsilon, and then you have this situation where this is C sub R and this is C sub C, but the pressure before, so this is sigma prime 0 V, and then the structure is going to create, so structure, the building that you're building, creates an increase in stress, equal to delta sigma. So that means that before you put the structure, you had sigma prime OV, but after you're going to have right here, this value is going to be sigma prime OV plus delta sigma. If this sigma prime OV plus delta sigma doesn't reach the pre-consolidation pressure, you have a certain behavior, a certain equation. If, on the other hand, your sigma prime OV plus delta sigma reaches a point where you're in here, then you have both this recompression behavior and a virgin behavior that you're going to have to take into account. All right, so let's see now how we can calculate the settlement of a structure. I gave you an equation, which is the elastic equation, and it's a simple equation that's quite useful. But there's a general approach. So general approach for settlement calculations. And there's a number of steps, and I'll go through those. One, find the depth of influence. We'll call that Z sub I. In other words, if you have a certain structure with a certain width, how far is the soil going to feel the influence of this new load? How deep down? 2, divide Zi into a number of layers, soil layers. Typically minimum 4, maximum 10 if you're going to do by hand calculations. 3, calculate the vertical effective stress in the center of each layer. We'll call that sigma prime 0 vertical. That's the one before any load is applied. 4, calculate the increase in stress due to the load. We'll call that delta sigma. That's what I was talking about on this consolidation curve beforehand. 5, find, well, let's put a step that's going to be independent here. 5, select a stress strain curve for each layer. Six, obtain so this is a stress strain curve that's going to be stress versus strain, and for each stress you're going to have to find the corresponding strain. Obtain the strain epsilon B4 corresponding to sigma prime OV. So when you had sigma prime OV, you had a certain strain, and then obtain the strain epsilon after, so I should say here, in each layer. And then the strain epsilon B corresponding to sigma prime OV plus delta sigma in each layer. So if you prefer, because we have n layers in here, so all these values are sub I, sub I, sub I, sub I, and there's some running indices for each one of those things, because we have several layers. Step 8, calculate the compression of each layer as delta H equals H0 times epsilon after I. So H0I, delta HI, there's I everywhere. BI, so that's the compression of each layer. And then finally, the settlement is the summation of all the compression. The structure, the settlement of the structure is settlement equal sum of delta HI. So it's a very general approach that works in all cases. And there are a number of important steps here that we need to discuss. And I won't have time to cover everything, but the one thing I want to cover is this Z sub I here. Z sub I is the depth that, so you have a certain structure that has a width B, and then you have a certain Z sub I, which is the depth to which the soil is going to be compressed due to this additional load here of width B. And then there's a certain length in that direction, you know, that structure is something like this. There's the length L and the width B. We take Z sub I equal to 4 minus 2B over L. Okay, so it's a simple equation that gives you an estimate of how deep the zone of influence is going to be. So if B is equal to L, if you have a square foundation, you have 1, 2, 4, so ZI times B. Here I'm missing something. So 4 minus 2 times B. So if you have ZI, if B is equal to L, and this is 1, so you have ZI equals 2B. So the depth of influence below a footing that's square with a B width, it's going to be 2B. If you have an infinite long footing, so B over L is 0 because L is very large compared to B. So this is 0, 2 times 0, you have 4B. So if you have a strip footing, a very long footing with B, the depth of influence is going to be 4 times the width of the footing. So I'm going to stop right here, and then the next lecture, when we start, we'll start talking about the increase in stress and the selection of the stress-strain curve so that we can we're able to calculate the settlement of these large structures like the, now, the case of the BURJ KHALIFA, we don't do calculations. Well, you can do calculations like this. There's nothing wrong with it. But typically it's done by finite element method because obviously, because of the scale of the project. But this method is a very general method that works, and it includes the solution that I mentioned to you with the elastic solution. And so next time we will talk about stress increased with depth, which stress-strain curve to select to solve the problem, and then we'll talk about the consolidation theory and how we can predict the time that it takes for all that settlement to take place.